Hello everyone. In this video we're going to talk about tensors, the essence of TensorFlow. So what is a tensor? A tensor is a generalized vector, right? So a tensor rank 0 is a scalar, a tensor rank 1 is a vector, tensor rank 2 is a matrix, and so on and so forth. And so why TensorFlow is using tensors instead of what? Instead of just the arrays that we have in NumPys. So because arrays are a fundamental data type that we have in Python, especially when you want to use them in Python, use the NumPy library. And they are really good for basic numerical calculations, but tensors are very similar in essence to arrays, but they're optimized for numerical calculations that you need in machine learning. Okay, and I'll tell you what do I mean by optimize. Where is it? So let's look at three major differences between TensorFlow's tensors and NumPy arrays. One is tensors in TensorFlow, they can be used natively with GPU and TPU, okay, and this is a capital U, right? But the arrays that you have in NumPy, they are not natively made to be used along with GPU or TPU. They are used with CPUs typically, unless you add some extra libraries. So you see, tensors are just optimized for machine learning and deep learning specifically. Tensor constants are immutable, okay? And arrays can be changed, but tensors are not. We'll get to this. Tensors have something called automatic differentiation. That's one of the things they have for optimization, also for machine learning. Differentiation is used a lot in machine learning when the system is being trained. Okay, when we use methods like steepest descent, like gradient descent, we are always taking derivatives of some function, whether it's cost function, activation function, or something with respect to some variables, right? And so this automatic differentiation is something that is available for tensors, not for arrays. Now, what is automatic differentiation? Automatic differentiation, or AD, is a family of techniques similar to backpropagation that we have in neural networks, and that is going to be the topic of one of our future videos, backpropagation. But it's more general and more efficient and accurate when it wants to calculate the derivatives numerically. Okay, so if I have time, I maybe, hopefully, I try to add a video about automatic differentiation techniques, at least one of them, something that you see, okay, and understand. So this automatic differentiation is an optimized, more accurate method for taking the derivatives, and that you can use with tensors, not with arrays. Okay, so how do we create these TensorFlow tensors, right? So here I import TensorFlow as TF and NumPy as NP. And so let me show you special tensors first. So if you want special tensors, one of them is TF.0, okay? If you use TF.0, then you can get a zero matrix. Just like in MATLAB, you have the command zeros, or in NP, right? NumPy, you have NP zeros. In TF, you also have TF.zeros. And you can give it a shape, right? Which is basically the size of the matrix, and the type of the variable, D type. So here I'm saying the type of variables are unsigned integer with 8 bits, and the shape is 5 by 4. Then I can use the command print. So you see here, all the code is written in Python. Give it to me and go to the next line. Or instead of uint8, I can ask for another data type, float32. Now they're going to have decimals and 32 bits. Okay, or I can ask for complex numbers. Now they're going to have a complex portion, and there will be 64 bits per each one. Okay, so let me run this and show you these first three matrices. So you see here, this is a 5 by 4 TensorFlow 0 matrices. The data are all integer, unsigned. Here is the one that was 32. So you see there is a dot, a decimal dot added, because now they have decimals. And in this case, they are 0, but in general, they could be non-zero. And when we said complex, now it's 0 plus 0j. You see, both real and imaginary parts are floating points, and you also have a what? A j. So in general, when you want to define a complex number in TensorFlow, you say like 2 plus 3j, 3 plus 4j. You use j, you don't use I, and you don't need to say 3 times j. You don't need to use asterisk or anything. You just say 3j, okay? So you say what? 2 plus 3j. In MATLAB, you say what? You say 2 plus 3 times j, or you can use 2 plus 3 times I. You don't use any of that here, okay? You just use j, and there is nothing between the number and the j. Okay, you can have a matrix with all ones. Again, all you need to provide here is the shape, right? All you need to provide is the shape. Now, do I need to say shape equal to? Not really. If you don't say that, it knows that's the shape, and you don't even need to say any D type. If you don't, look what happens. There automatically will be float 32. You see, so if you don't say a type for your variables, the default in TensorFlow is float 32. Okay, and it knows the first matrix that you provided is really the shape of it. So if you don't provide that extra information, you still can get all these ones in the matrix. What other special matrix do you have? Can you have identity matrix? Yes, tf.I, you provide one number, which is basically a square matrix, so it's 3 by 3. And again, you see, again, float 32, and that's a 3 by 3 identity matrix. The other thing is a diagonal matrix. So here you have to go to a sub-library of TF called linear algebra, and there you have the method called diag, and you pass to it the diagonal elements, and so it creates a 3 by 3 and put 5, 7, and 8 on the diagonals, as you can see over here. Now, interesting type, look here. When you use that linear algebra.diag, look at the default type. It's integer 32. You see? So the TF itself, default, if you don't say it, is float 32, but for that linear algebra is int 32. Okay, so these are some interesting observations. And another interesting thing you can do is this command called tf.zeros underscore like. What does like mean? So here, instead of passing it a bunch of numbers, you pass to it another matrix. You say, hey, I want a matrix like this matrix called ones.mat, which was a 4 by 3. I want a 4 by 3. When you say like, means the same size. I want a matrix just like that, 4 by 3, but fill it with zeros. So look at this last one. You see? It made this similar to this one, the same size, but filled it with zero. And you can say ones underscore like as well if you want to. Okay, so we also have ones like. Okay, so this like is basically means copy the shape, fill it with the numbers I'm telling you. Now, can you create a matrix, an array, something from NumPy and then convert it into a tensor? Yes. So here I created the NumPy matrix 1, 2, 3, 4, and I used the command tf.convert underscore to underscore tensor, and I will convert it into a tensor and then I show it. Okay, so you see tensor 1, when I show it, look, 1, 2, 3, 4, and look at the type. Interesting, int 64. Okay. Yeah, and you can see all of these variables here. When you run that, you can see all of these variables, right? And you can see that, for instance, here, NumPyMat and Tensor1. Let's look at them. So you see NumPyMat is ND array 2 by 2, but Tensor1, if you look at it, it's what? It's eager tensor 2 by 2. Now, what is eager? I'll tell you, but just want you to see that, yes, I can literally create something in NumPy and then what? Convert it to TensorFlow. So 2 questions. 1, If I don't want to do that, if I directly want to define this matrix in TensorFlow, okay, a tensor like that, 2 by 2, by providing the numbers row by row, can I do that? Of course, I'll show you. Second, what is eager? So let's talk about eager first. So in eager mode, let me read it and explain it. Operators in a model are immediately executed when they are encountered in graph mode, which was in TensorFlow 1. Operators are first converted into a graph, and then at the end, they will be compiled and executed. So this graph mode, it was in TensorFlow 1. In TensorFlow 1, what we had was we call it the graph mode. And so when you have all this code, yeah, it will all be converted into a graph, and the numbers will not be placed into the graph until the very end. When you compile, then all of these numbers will be placed into the graph and then will be executed. While here, you can basically part by part, you can run, you can see the results, and you can move forward. So it's much better for debugging compared to that graph mode, which was good for speed maybe, but here the goal is to ask TensorFlow to eagerly execute the code and see the results right away. Okay, and as I said, it's by default active. If you want to make sure it is, you can say tf.executing_eagerly answer, and this answer is true if the default mode is eager execution, and it's false if the default mode is what? The graph execution. So if I run this, you see the answer is what? True. Yes. TensorFlow 2, which I'm using right now in Google Colab, has a default of eager mode, means immediate execution of the code and seeing the results, okay, which is really good for debugging. So this is eager thing. Now, as I said, how can you create a tensor by just giving the numbers, right? And not creating it in NumPy and converting it to a tensor. How can I do that? Well, one simple thing you can do is tf.constant. So you say, hey, I want this A2 matrix or tensor, and it's tf.constant, and just like NumPy, you provide what? A bracket, and then inside inner brackets, you provide the rows. So if I run only this line of code, what's going to happen is I'm going to create a 2. Let me show you. Now it has an error, I know that, so let me basically comment this line out so you can see it. And also this part. Okay, and let's run. Let's see. Okay, look here. The result that I'm showing is, if you can look at it, 2316, right? Which one is it? It's A3, which is with variable. But if I want to show that one, I can simply say what? Print A2, right? So now take a look here. You see? Here. That's A2, and it is 1, 2, 3, 4 shape 2 by 2, D-type inter 32. You see here? So this is how I can create a what? I can create a tensor with given numbers, and I can make them constant or variable. I'll get to that in a second, but that's how you do it. But before that, I have to warn you about one important thing. A tensor can only have one type of data at a time. So if you want to store different types of data under the umbrella of one tensor, you cannot do it. So here, I want to store 2 numbers and a character or string under one tensor. Look, here, you're going to get error. And it tells you that, hey, I cannot convert Python sequence with mixed data to tensor. So you cannot do that. Now, you might say, what if I get rid of this A? If I get rid of A, if I have a different variable type, I mean storage type, right? Like one and an integer and a non-integer. Would that do it? Yes, no problem. These are numbers. These are numericals. Okay, right? You see here, you did not get any error. Now, what is that result? If you want to see that, you can print it, right? If you print that, look, what's going to happen? Let me explain that also for you. That's interesting. What happened? I had an integer and I had a float. It will converted both of them to float. So it will go to higher number of bits per storage for all of them, okay? And store them all with the same data type, float 32. Yes? But again, if I bring this guy back, guess what? It's not going to be able to do it for me, okay? It's not going to be able to do it because I have different types of data. Okay, so going back to tensor constants and tensor variable, what is that? One properties of tensors that I mentioned up here is that tensors are immutable. What does that mean? It means you cannot change them. So here, look, if I create a NumPy array, 1, 2, 3, 4, and then say, hey, change 1 and 1, which is this element here, change it to 5, would that do it? Look. Yes. You see? No error. Let's print A1 so you can see that. Right? No error. It could easily convert. Look here. You see? It changed that element 4 to now to 5. So you see this NumPy array is mutable. You can change it. But now look at this tensor. Here I create a tensor TF constant with similar numbers. And now I want to do something to it. For instance, I want to say the same thing. A2, 1 and 1 equals what? Equals 5, huh? Yeah? I want to do that. So look, let me do this first and see if we can get any result. So now I want to change that element to 5 and get the result. See if you can do it. You see here, you got the error. And what does it say? It says the tensor object does not support item assignment. You cannot change it. So what can you do? You have to create a new tensor. You have to create it from scratch again and define that 4, change it to 5. You see, this one cannot work. And it's not just that. You might say, what if I use the command assign and change it? Can I do that? Can I use the command assign? The answer is again what? No, you can't. Okay, because assign here I say change A2 dot assign to 2, 3, 1, and 6. Instead of this guy, change it to this one. Change the whole matrix. Change a bunch of them or all of them. Can you do it? Look. Again, error, right? You cannot do that. Okay, it's not possible. So assign is not working with constant tensors, right? What about variables? If you have a variable tensor, can you do it? Yes. These are the tensors that during the program execution, their values would change. So if you want something to change, you say tf.variable with cap V, and you can either type the values in, just like we did earlier, or you can pass a variable that was once a constant tensor. If you pass it to variable, now the new variable you get is a variable version of that. So look here, A2 was constant, we cannot do anything. Now I pass that A2 to TF variable, call it A3. A3 is now variable. So look, if I pass the A3 assign and try to change A3, look what happens. A3 should be basically okay with allowing me to change it. Look, here we go. See, A3 allowed me to change. Okay, so these are all important things I'm telling you about tensors. You cannot mix the data, and you cannot change them if you define them as constant. If you want to change them during the code, you have to define them as a variable. And of course, you can create them in NumPy and convert them to tensor using what? using the TF convert to tensor. Now, one question you might ask is, when I convert to a tensor, right? When I convert to a tensor, would the result be a constant tensor or a variable tensor? So if I go and look at tensor again, look, tensor 1 is an eager tensor 2 by 2, right? If I go back and look at these guys, remember A2 and A3, they are both tensors, one of them variable, one constant. Let's go back. Look at the difference. The constant one is called eager tensor. The variable one is called what? Resource variable. So what did this command do? What did this command do for you? This convert to? Let's find it. It's too much stuff. I did over here. Here, this guy. What does it do? It converts the array into a constant tensor, not a variable one. Be careful about that. Okay, let's move on. So, what else can you do? So you might say, if I want to create an array with equally spaced data, like the linspace or the column operator that you have in MATLAB, right? Or the linspace in NumPy or the arrange in NumPy, what would you have here? Well, I'll show you. So one command that you can use is tf.linspace. You can use tf.linspace, and you can pass to it the start, the stop, and the number. So if you say start 0, stop 1, and number is 11, it is going to create 11 numbers between 0 to 1. Or you can use the NumPy linspace and what? Convert it to the tensor. Both of them are going to what? Are going to work. By the way, TensorFlow does not have pi. TensorFlow does not have pi. If you want pi, you have to get it from NumPy, or you might get it from TensorFlow under math.math. So be careful that you cannot type in tf.pi. There is no such a thing. Okay? If I here say, hey, print for me tf.pi, what do you think would happen? You see? There is no pi in TensorFlow, so be careful about that. But you can always get it from NumPy, and you can convert it here. You see, I converted it into a constant, right? I converted NumPy pi into a constant and call it pi. So now this pi is a constant tensor, that a scalar that I can use anywhere that I want. Okay, yeah. So I showed you the linspace command, whether from NumPy and convert it, or directly from what? From TensorFlow. And for data that you have the increment, not the number of data, again, either you use np_arrange and convert it to tensor, or you can use the command tf.range. And the format is start, limit, or the end number, and delta, the increment. So here I'm going to create numbers between 0 to 1 with increment of 0.1. So this is another way to create equally spaced data. Here you know the increment, here you know the number of data points. Okay, so these are what? Equally spaced data, and you can see that the first one I did, I created 10, 11 numbers between what? Between 0 to 2 pi. And I got here, and the second part, I created a bunch of numbers between 0 and 5 with increment of 0.5 here, right? So even if I call this portion like that, and I comment this out, and I comment this out, and I run it, I should get the same result. See? So here I use the range command instead. That's the same thing. The only thing is, let's see, here I have to show this actually. Let's do it again here. Okay, look, you see? Constant increment of 0.5. What's the problem? The problem is this. you never go exactly to 1, right? You go 1 increment below 1. So the command range and arrange are similar, okay? This one, remember, it didn't go to 5, it went to 4.5. And here is a similar thing. And another interesting thing is this. Look at the last number. There is some error here, really. Okay, it added that 4 times 10 to the negative, what is it, 9, I guess. It added it by basically probably it's a rounding error or something. Okay, it should get rid of that, but it didn't. So that's why I think here I would rather go with this one. Not that it really creates an error every time, but you see here, at least I don't see error over there. And you might say, well, if you change your numbers, maybe you will. Well, let's try that, see what happens. Okay, so here we go like that. Let's see, you see, no, it didn't. Okay, what else? Can we have random numbers? Sure. One thing you can do is tf.random.uniform. These are numbers from a uniform distribution, and you give them the size of the tensor and the min value and max value. And so here you can really remember in MATLAB the numbers, when you use the command rand, they are always between 0 and 1. Here you can say to generate them between any number to any number. So here I want them between 0 and 2, let's say, or 1 and 2, or whatever, any number. I want them between 2 and 5. So it's fine. It is going to generate that for you. Yes? Okay. And you can have them. Can you get them from a normal distribution? Yes, you can use tf.random.normal. Again, size of the tensor, the mean, and the standard deviation. So here I want mean of 0, standard deviation of 2. And if I do that, look, these are all the numbers between 0 to 2, size 3 by 2, as you can see. Here, these are the numbers from a normal distribution, mean 0, standard deviation 2, and clearly you see they can go negative, and they can be more than 2 standard deviations off. They can be more than 2 standard deviations off. There is another one under normal, is called truncate. I don't go through it, but you can search it. It's called .truncate. That one only generates number from mean plus and minus 2 standard deviations off, not more than 2 standard deviation. So this one can go more than 3 standard deviation. There is no limit here. Of course, the chance goes down of generating such numbers because it's a normal distribution, but it can generate that, as you can see here. Okay, you see here, this is more than 2 times 2 off. But the truncate version of this, it only goes plus minus 2 standard deviations from the mean. Can you generate some vectors from some specific order like these and then shuffle it randomly? Yes. There is this command called tf.random.shuffle, and you can pass to it something that's like this len array 2. That was a bunch of numbers between 0 to 0.9, and ask them to what? To shuffle it for you randomly. And you see here, all of those numbers between 0 to 0.9 are shuffled randomly. Look at the order right now, 0.8, 0.6, 0.9. If I do it again, look, you will not get the same thing. You see? Because it's a random shuffling. Okay, so this random shuffling is an interesting feature that might be useful it will be useful in machine learning. Okay, the last 3 things I want to talk about are these interesting stuff. One of them is string, the other one is called ragged tensors, and the other one is called sparse tensors. So let me show you these. And for string tensors, you can use the command tf.constant, and you pass to it the string. And look at the interesting thing. If you do that, right here, I'm passing the entire hello world exclamation mark to it as a constant. So if it was in an array in Python or MATLAB, it would consider it an array of characters. So it will have a length of 12, and then this is like the character 0, this is character 1, character 2, 3, all the way. But here it deals with it as one single entity, and it's a string, and it's the whole thing. Look here. Look at the shape. The shape is empty parentheses. What does that mean? This is another thing I need to clarify for you. Whenever you see for shape of a variable, you have empty parentheses, that means it's a scalar. If it only has one dimension, it doesn't say 10 and 1, 11 and 1. It just say 11, 10, 10. If you don't see a second dimension, just the first dimension and a comma, that means it's a 1D array. If it has two dimensions, now it's a matrix. Okay, so 1D arrays only have one value under shape and a comma, and the scalars have none. Okay, pay attention to that. These are some major differences. So you see here, the shape of this whole thing is empty. That means what? It's just a single scalar. So if you want to define it as two separate words, then you have to have them in a bracket like this. You have to put them in a bracket and separate hello and word from each other. Then you see the shape is 2 and nothing, which means basically 2 and 1. You see that? And it's interesting, behind each one of these words, it puts a what? It puts a B, and B here means byte. B here means byte. So each one of them is allocated a byte. Okay, sparse tensors. Sparse are the ones that not all of the matrix has non-zero values. A lot of the entries are zero, only a few of them are non-zero. And the way you want to define it is using tf.sparse tensor. What do you pass to it? Under indices, you tell it where the non-zero values are. So you say 0, 0, which means the top left element, and then 2, 1, which means third row and second column. What values would sit there? 2 will sit in the first location, -3 will sit in the second location. And what's the shape of this guy? It's a 3 by 4. So it's a 3 by 4 zero matrices, except for two locations which will get to a -3. You can see that here, right? Look. You see? Okay. Now, one interesting thing is this. Can I convert a sparse tensor to a regular tensor when I create them? Yes. This, because it is a real tensor, it doesn't care how many of them are zero or not, so it can convert them into a regular, or what we call a dense tensor, using the command tf.sparse.toDense. So you can convert them into what? Regular, or you might call what? Dense tensors. All you need to do is to pass them to this command, as you can see, and it is going to do that. So if I run it one more time for you, you see, first, when it was created in this print, look at that. You see, it has a lot of information, which is for a dense tensor. But when you create it, and look here, this is how it is shown, right? But when you create it into a regular tensor, it just shows it as a regular tensor. Okay? Another very interesting thing about tensors is, which you don't have like in MATLAB, if you have an arrangement of numbers that is not rectangular, so the number of elements in the rows are not the same. Some rows have like 5 columns, some rows have 2 columns or 1 column. Can you put them together under the same umbrella? Yes, it's called a ragged list or a ragged tensor. So here, look, my first row has 4 numbers, my second row has 2 numbers, third row has 1 number, and last row has 3 numbers. I create that with what we call, it's a list, okay? It's a list, and then I convert that list into a ragged tensor using the command tf.ragged.constant. And I convert it into a ragged what? A ragged tensor, and I can show it. The only problem is If you want to convert it into a dense tensor, you cannot do that, because in order for it to happen, you have to have the same number of columns in all rows. Okay, so you see here, right? Look, it did create the ragged tensor, but it could not convert it into what? Could not convert it into a dense tensor, right? So here, let me comment this line out for you. You see, it did create it for me, but again, you cannot convert it. Okay, so hopefully this video was useful to you. It was a little bit long lecture, but I told you some very basics about what tensors are, what's the difference between them and arrays, how to go from arrays to tensors, and what are the advantages of them, what's the eager execution, and how to create specific types of tensors, random, special ones, equally spaced, strings, sparse, ragged, the fact that you cannot store different types of data, and so on. So hopefully it was useful to you. I'll see you in the next lecture.